So for this class, we will create a simple case study involving a straight channel that is 2500 meters long and conveys a discharge of 0.5 cubic meters per second. The channel has a bottom slope of 0.001 and a Manning's end value of 0.03, representing the channel's roughness. Both the upstream and downstream cross-section have trapezoidal shape with the dimensions shown in the figure below. This is for the downstream side and here is for the upstream side. So the river flows from the east to the west. To create a new project, let's click on File, New Project. And let's go to our default project folder and create our folder for our new project. Let's call that simple case 01. And then we need to give our project a title. Let's call that simple channel. Click OK, and yes, we would like to create a project using SI units. And the next thing to do is to create channel geometry. We are going to do that by using this view or edit geometric data. And the first step is to create the river ridge. Let's click on the top left corner. And to add a new river, we need to start from upstream to downstream. So let's click on the upstream side and double click if you want to end drawing. So let's give our river a name. I would like to call that a straight channel. And I'm gonna name our ridge as main ridge. Once we have the river and ridge, we will create the cross section. Let's add a new cross section by clicking on these cross sections and then option, add a new cross section. The opposite with the river and ridge. To create a new cross-section, we are going to start, or we have to start from the downstream side to the upstream side. So the first cross-section we will add is the river station 0, or the most downstream side. Here we have already had the data from the survey, for example, the stations and elevations. We can type manually or we can copy and paste it. We have the Manning data as well for these examples. Apply data, that's it for the downstream cross-section. And we're going to draw or add the upstream cross-section. The river station is following the length of the channel. We also have the station and elevation data already there. Apply data and then click exit. Let's see, we already have the river cross sections for the downstream side and as well as for the upstream side. We also have assigned the channel roughness through Manning's end value. And I think we already throw the necessary data for the geometric data, and don't forget to save your geometric data. I'm gonna put original as its name in order to differentiate with the alternative or the design, or if we want to put some bridge and other structures, so we can put another name for that. Now we already have two cross sections in our river channel, one in the most upstream side and the other one in the most downstream side. Because our problem have only like one type of cross sections, so it is actually enough to represent our simple channel. But for the purpose of computation, these two cross sections representing 2500 meters length of channel is not enough. So we need to create many cross sections in between. We can do that by adding more cross section like our previous method, or we can do that by interpolating these two cross sections using GIS tools. Using these tools. The consideration is as follows. If our river have the uniform, like if our case is a uniform river channel, let's see this one. Both the upstream and downstream side both are trapezoidal channel with the exact same dimensions. So we can just do the interpolations. We will interpolate these two cross sections by using these tools, XS interpolations between two XS. So we will interpolate the cross sections between RS0 and RS 2500. Let's put the maximum distance between the interpolated cross section as 20 or 25. Let's do 20. Let's click on interpolate new XS and then close. Now we have many cross sections for the sake of computations. Let's save the geometry and let's check our profile, and that's all. The geometric data has done. Okay, having the geometric data ready, now it's time to input or assign the flow data. To do that, let's click on View or Edit Steady Flow Data, or we can access that through this menu as well. Edit Steady Flow Data, or just click here. In this problem, our channel conveys 0.5 cubic meter per second of discharge. If we want to add more scenarios on our simulation, we can also try what if our channel also convey 1 cubic meter per second at another time, or at another scenario, or at another simulations. We can run these two simulations together. This is for the upstream side. So normally for boundary condition we set river flow in the upstream and water level on the downstream. Let's click on reach boundary condition. Because we have no data of water surface elevation and our channel is not in critical depth as well, we don't have any data on the rating curve, but we have the slope data, so let's use the normal depth. Our river bottom slope is 0.001. Click OK on that. Click OK again, and let's save our flow data. We can call that flow 0.5 and 1. Okay, now we have the geometry, we have the flow data for steady flow simulations, and now we can run our model. To run the model, we can click on Run and click Steady Flow Analysis. We can also click on this menu. Perform Steady Flow Analysis. In each run, it is recommended to save the plan. So let's save the plan as original geometry and flow of 0.5 and 1. Steady. Click OK, and HEC-RAS will ask for short identifier. Let's call that as original 0.5. Or let's just call that scenario 00. Click OK, and because we only have one type of geometry, then it is automatically choose the one that we opened last time. And if we have more scenario, we can also choose another scenario, but this time we will run a flow of 0.5 and 1 cubic meter per second onto the original geometry. Let's try our model. Okay, the computation is finished, and now we can click close. After finishing our computation, now we can see the result of our running. To see the result, we can choose all of this menu is to show the result. Let's just check on those one by one. This menu is to show the result in cross-section. And then if we want to see the long profile, we can click on this. And please notice that we can also choose what types of variable that we want to see. How to display this menu is to right click anywhere inside this window and then click on variables. We can see, or we can select the energy grade elevation, critical depth elevation, filled in water surface, left main channel bank elevation, and right one. So this is the left and right bank elevations. Here is the ground level, and this is our water surface for profile number 1. So we have two types of profiles in our steady flow data. Profile 1 is 0.5 cubic meter per second, while profile 2 is 1 cubic meter per second. So we can also select all profiles. It means that when our channel conveys 1 cubic meter per second of flow, then the water surface elevation is gonna be this high. Or we can check on the cross-section data. This water surface elevation is resulted from the 1 cubic meter per second. Meanwhile, this one, the lower one, was resulted from 0.5 cubic meter per second. Here is the cross section, and this is the long profile. And by the way, the long profile in HEC-RAS in the result section will always flows from the right hand side to the left hand side. It has nothing to do with our geometric data. We can draw the geometric data from left to right, from up to bottom, or from bottom to up. The result, the profile plot, will always show from the right to the left. And then if we want more details of the calculation result, we can also see the tables. We can analyze in detail by looking at these numbers. Okay, so that's about it for the simple case and steady flow analysis. We will continue to the unsteady flow analysis or other a little more complex geometry tomorrow.